Hi, let's now move on to the last topic of this section, correlation amplitude and the energy-time uncertainty relation. We shall examine how state gates at different times are correlated with each other. Suppose the initial state gate at t equal to 0 of a physical system is given by ket alpha. Now with time, the system changes, it evolves into another state. Let's call the state at a later time, as usual, ket alpha comma t0 equal to 0 at time t. How do we obtain this? We can obtain this thing, as we have said many times, by the action of the unitary time evolution operator on the initial state. Now, how similar is this state at a later time t to the state at the initial time ket alpha? How similar are these two states? This is the question that we are interested in. Okay, so we want to quantify the extent to which the state ket at a later time t is similar to the state ket at t equal to 0. To quantify this, we can construct the inner product between these two states, because the inner product will give us the overlap between these two states. It will quantify how much these two states overlap. Okay, so we define the correlation amplitude C of t as the inner product between the initial state and the state at a time t. Okay, now since the state at a time t can be related to the initial state by the action of this unitary time evolution operator, we can write the correlation amplitude as bra alpha u of t comma 0 ket alpha. Okay. Now C of t is equal to bra alpha u of t comma 0 ket alpha is in general a complex number. So we can take the modulus of C of t and use it to quantify the resemblance between the state gates at different times. Okay, so the modulus of C of t provides a quantitative measure of the resemblance between the state gates at different times. Let's consider an extreme example. Okay, consider the special case where the initial state ket alpha is an eigenket of the Hamiltonian. All right, so let the initial state ket alpha be equal to ket a prime, where ket a prime is an eigenket of the Hamiltonian. Okay, now this means that the state at a later time can be written as exponential minus iht divided by h bar acting on ket a prime, the initial state. This is u of t comma 0. Okay, now since ket a prime is an eigenket of the Hamiltonian with the eigenvalue e a prime, we can write this as exponential minus I e a prime t divided by h bar multiplied by ket a prime. Now if you calculate the correlation amplitude, it is bra a prime. Okay, this is the state at the later time. So we find the inner product between bra a prime and the state at a later time. Okay, so the state at a later time is given by this. So it's bra a prime exponential minus I e a prime t divided by h bar. Okay, ket a prime. Now this is a number. Okay, this is a number, it can be taken out. So by orthonormality, bra a prime ket a prime is 1, and we get the correlation amplitude as exponential minus I e a prime t divided by h bar. Now what's the modulus of this? The modulus of this is 1. Okay, because this is a complex exponential minus I e a prime t. So if you take the modulus, you get 1. This means that the state has not changed. The system has remained in the same state. This is something that we expect for stationary states. Okay, we have already seen this. So if the state does not change, the correlation amplitude or the modulus of the correlation amplitude is 1. That's the maximum. Okay. If the modulus of the correlation amplitude is 1, that means that the state has not changed at all. Let's now consider a general situation where the initial ket is represented by a superposition of energy eigenkets. Okay, that is, let's take the initial state as a superposition of energy eigenkets. Right, we'll take ket alpha as sum over a prime, c a prime, ket a prime. Now we know how to calculate the state at a later time. So the state at a later time is simply get alpha comma t0 equal to 0 at time t. This is equal to, here we have already used the summation index a prime. So let me use a different summation index a double prime. So we will have c a double prime exponential minus I e a double prime t divided by h bar multiplied by get a double prime. Okay, so this would be the state at a later time. Now we can find the correlation amplitude bra alpha get alpha comma t0 equal to 0 at time t. Okay, we just take the inner product between these two expressions. So this is get alpha. We have to find bra alpha. Bra alpha would be sum over a prime c a prime star bra a prime. Okay, and we just now substitute get alpha comma t0 equal to 0 at time t. So that is sum over a double prime c a double prime exponential minus I e a double prime t divided by h bar acting on multiplied by get a double prime. Okay. Now we can bring the numbers together. So there are two summations. One is over a prime and the other one is over a double prime. We have got c a prime star and c a double prime. These are numbers. We also have this number which is exponential minus I e a double prime t divided by h bar. Okay. And then we have a bra a prime from here and get a double prime from here. Now we use the orthonormality property. So this bra a prime get a double prime is delta a prime a double prime. So instead of this, let me simply write the Kronecker delta, delta a prime a double prime. Now you carry out the sum over a double prime. Okay, so the all terms will become 0 except the term for which a double prime is equal to a prime. So the summation is lost because there is only one term that is non-zero in the entire summation. So this becomes sum over a prime, c a prime star, c a prime exponential minus I e a prime. So the a double prime will become a prime. Okay. Now what is this? This is modulus of c a prime square. Okay, so we can write this as sum over a prime modulus c a prime square exponential minus I e a prime t divided by h bar. Okay, that's the result that we have here for the correlation amplitude. So the correlation amplitude is sum over a prime modulus c a prime squared exponential minus I e a prime t divided by h bar. Okay, so this is the correlation amplitude in the case where the initial ket is a superposition of energy eigengets. Okay. This expression for the correlation amplitude is a sum over many terms, and each of these terms has an oscillating time dependence. Okay. So you see that each of the term has an oscillatory behavior, but the frequency of oscillation is different for each term. Also, as time increases, the what do you say, the oscillations also become more and more rapid. So actually we are dealing with a large number of oscillating terms, okay, with each oscillating with a different frequency. In this case there would be large cancellations for moderately large values of t. There will be strong cancellations for moderately large values of t. Okay. Now, if you look at t equal to 0, the correlation amplitude at time t equal to 0 is simply sum over a prime modulus c a prime square. Just put t equal to 0 in this expression, and this is equal to 1. This is just the normalization condition. Okay. But as time increases, we'll be adding up terms which are oscillating like this, and because of these cancellations, the correlation amplitude will start dropping from 1. So we expect the correlation amplitude that starts with unity at time t equal to 0 to decrease in magnitude with time. All right. Now, as the oscillations become more and more rapid, it will quickly go to 0. The correlation amplitude will quickly go to 0 because of the strong cancellations between these oscillating terms. Okay. We can now estimate the correlation amplitude in a more concrete manner. For this, let us suppose that the energy eigenvalues corresponding to these eigengets or our basis vectors are not very different from each other. Right? We assume that the energy eigenvalues, let's say E a prime, EA double prime, EA triple prime, etc. These are not very different from each other. They are similar. So if these different energy eigenvalues are very close together, we can use the mathematics appropriate for continuous spectrum. Okay, instead of discrete, we can use the mathematics appropriate for a continuous spectrum. Okay, so we can regard these eigenvalues as exhibiting a quasi-continuous spectrum. All right, it's not exactly continuous, but if they are really close together, we can think of it as exhibiting a quasi-continuous spectrum. Okay, and in that case, we can use the mathematics appropriate for such situations. So instead of summations, we'll have integrals, etc. If we treat the eigenvalues as continuous, then the summation over A prime can be replaced by an integral of this form. Here, rho of E characterizes the density of energy eigenstates. Let me explain what this means. Let me represent the entire energy range by a line like this. Okay. So this is the entire range of energy that we are interested in. Now this range can be divided up into equal pieces. Let me divide this range up into equal pieces, each of width delta E. Okay, so each of these pieces, each of these intervals has a width delta E. So suppose this is the energy E, then this would be E plus delta E. Okay. Now corresponding to each interval, there will be a number of states. Right? There will be a number of states corresponding to each interval. Okay. Now clearly, the number of states will be proportional to the width of this interval. Because if we take a larger interval, then the number of states also will be larger. Okay. So we need an expression for the total number of states in a given energy range. Okay, or in a given energy interval. Okay. So we know that the number of states, or we can write this expression like this, the number of states with energy E and E plus delta E. Let's say energy between E and E plus delta E. All right. This is clearly proportional to delta E because more the width, more would be the number of states. This is proportional to delta E. Now we can write this as an equality by introducing a proportionality factor rho of E. All right. So this is what the density of energy eigenstates means. The proportionality factor is written as a function of energy because the number of states at this in this region need not be the number of states in a different region. In general, the number of states can depend on the value of energy. All right. So in general, we write this proportionality factor as a function of energy. All right. So rho of E is defined in such a way that rho of E multiplied by delta E gives the number of states between energies E and E plus delta E. Now let's consider a summation of this form, sum over A prime of some function of energy. All right, so this you have to sum this function over all energy eigenvalues or all energy eigenstates. Okay. Now instead of doing this, I can make an approximation. Right, I label each of these intervals as 1, 2, 3, etc. In general, we'll give it a label I, the ith interval. Okay. Now what we do is that we evaluate the function at corresponding to a particular energy in this interval, in the first interval. All right, and then we assume that the function, the value of the function is the same for all states within this interval. All right, or we assume that the value of the function does not change considerably over this integral. All right, so in order to sum over f of E or f of E A prime, we group the different states. All right, we put different states into different groups. This is the first group, this is the second group, etc. All right, and we make it into groups in such a way that when we go from one state to the next state within a group, the value of the function does not change considerably. All right, so let's first sum it over this interval and then sum it over this interval, etc., and then add all of them up. All right, so within this interval we can write this as f of uh, the value of the function at this corresponding to this energy plus the value of the function corresponding to this interval, etc. But we are now making an approximation. We'll say that this is equal to f of E1, okay, corresponding to this value of energy. All right, and we assume that the value of the function is the same for all these states. Then we multiply it with the number of states. Let's say that the number of states are 4. All right, so here I have drawn 4 states. Okay, so what we do is that instead of summing over all states in here, we evaluate f of e or f of e1 at a particular point and then assume that the value of f of e does not change within this interval. So instead of adding all this up, we just multiply f of e1 by the number of states in here. Okay. So instead of this, let me write it in general as f of e1 multiplied by the number of states has an expression rho of e1 multiplied by delta e. Okay. Similarly, now let's go to the next interval. Right. Here also we evaluate the function corresponding to some energy value and then assume that it does not change considerably over this interval. Okay. So now you evaluate f of e2 and assume that this is the same for all the states within this group. So you have to multiply it with the number of states here, which is rho of e2 multiplied by delta e plus etc. So if you do this for all groups, you would get this sum over a prime f of e a prime to a good approximation depending on how big delta E is. You can improve this approximation if you make delta E infinitesimally small. If you make delta E smaller and smaller, this approximate result will become more and more accurate. Okay, so in the limit where delta E becomes very small, this summation is just an integral. All right, this becomes an integral f of E multiplied by rho of E dE. Okay, so the sum over a prime f of e a prime can be written as integral f of e rho of e dE. Alright, so that's what this replacement means. The sum over a prime can be replaced by integral dE rho of e. That's exactly what we have done here. Okay, I hope this idea is clear. The expansion coefficient Ca prime is the probability amplitude for measuring an energy value Ea prime. So if we go to continuous spectrum, we can replace it by a continuous function g of E. Right? So it gives the probability amplitude corresponding to an energy value E. So if you want the probability for energy value Ea prime, if you want the probability amplitude for Ea prime, you just evaluate g of E at E equal to Ea prime. Okay, so Ca prime can be replaced by a continuous function g of E. Okay, let's now put it all together. This is our expression for the correlation amplitude that we first wrote. It's sum over a prime modulus Ca prime square exponential minus Iea prime t divided by h bar. Then we said we would go to a continuous spectrum or a quasi-continuous spectrum. In that case, we said we have to substitute sum over a prime by integral dE rho of E and Ca prime by g of E. All right, so this integral now will become integral. So sum over a prime is integral rho of E dE. All right, and Ca prime square now becomes modulus g of E square. All right, and then you also have, so instead of this discrete index, we'll simply write it exponential minus IET divided by h bar. Okay, so in this quasi-continuous limit, C of t becomes integral dE modulus of g of E square rho of E exponential minus IET divided by h bar. Okay. In discrete case, the normalization condition is written as sum over a prime modulus Ca prime squared is equal to 1. This means that the sum of probabilities over all possibilities has to be equal to 1. Okay. Now again we can find the corresponding expression if the eigenvalue spectrum, if the spectrum is continuous. All right, we just make the replacement sum over a prime is replaced by integral dE rho of E and Ca prime is replaced by g of E. Okay, so this becomes integral dE rho of E modulus square of g of E is equal to 1. The logic is exactly the same as we have already seen. Okay. Let's now get back to correlation amplitude given by this expression. Okay. Clearly, the value of this integral depends on the function modulus g of e squared multiplied by rho of e. Let us look at a specific form of this function. So let's assume that this function modulus g of e squared multiplied by rho of e is peaked around e equal to e0 with the width delta e. All right. So far away from e0, let's say that this function has value 0. So we are looking at a function like this, modulus g of e squared rho of e plotted against e. Okay. So let's say that it is peaked around e0. So everywhere else, okay, or far away from e0, it has value 0. There's a non-zero value only around e0, and let's say that this has a width given by delta e. Okay, so we are assuming that this function has a Gaussian form with the width delta e. Okay. Now this choice of the function, or the choice for this form of a function, is not completely arbitrary, right? This is what we see in a realistic physical situation. So in a realistic physical situation, this function actually has this form, all right? So let's assume that the function has this form, and let's see what happens to this integral, okay? We started with this expression for the correlation amplitude, and we chose a specific form for this function. We said that this function is peaked around E0 and it's 0 far away from E0. Okay. Now, since the energies are 0 far away from E0, E0 is an important reference point. Let's include it in this integral. Right? So all we need to do is to write this exponential minus IET divided by h bar as exponential minus I. Let's write this as E minus E0 plus E0. Okay, we just add and subtract E0 to the argument here. T divided by H bar. Okay. Now this can be written as exponential minus I E0 T divided by H bar multiplied by exponential minus I E minus E0 T divided by H bar. Okay. And this term can be taken out of the integral. Okay, so if we do that, we get C of t in this form. We have exponential minus I E0 t divided by h bar, which is this term, and then dE modulus g of e square rho of e, and then exponential minus I e minus E0 divided by h bar t. I have done one more thing. The t in the numerator here, I have taken it to denominator and I wrote it as h bar divided by t. That's all. Okay, so this t in the denominator can also be written as h bar by t in this form. Okay, so with this modification, the expression for c of t becomes like this. Now notice that I have also included a limit for this integral. Okay, now the limit of the integral is chosen because we chose a particular form for this function. Again, we said that in the entire energy range, this function is peaked only around E0, right? So at all these points, so we have got E0 here, everywhere else it is 0, all right? So let's say that this, it falls to 0 roughly at a distance delta, okay, in an interval delta from here. So we need to integrate, even though the integral is over the entire energy range, all right? There's a non-zero contribution only between these points. Okay, so we need to integrate only from E0 minus delta to E0 plus delta. The integral is 0 everywhere else anyway. Okay, so we don't have to integrate over the entire range. So let me write this as integral E0 minus delta to E0 plus delta. Okay, now what does this mean? This means that because of the specific choice for this function, all right, the integral has become 0 everywhere else. Okay, that's what we mean when we introduce the limits of this form. All right. So the form of this function has killed the integral everywhere else except in this small region. Okay. Now let's look at the behavior of this integral. Let's look at the second function. All right. Now if you look at this integral, this has the form of the product of two functions. So we are integrating the product of two functions. Okay. Let's look at the second function. We talked about the form of the first function. Let's look at the second function. The second function, exponential minus I e minus e0 divided by h bar by t. So let's look at this function. Exponential minus I e minus e0 divided by h bar multiplied by t. Okay. Now at t equal to 0, this is 1. But as t is non-zero, when t increases from 0, we see that we have an oscillatory function. All right. And when t increases, let's put this t in the denominator, so it becomes h bar divided by t. So as this term becomes bigger and bigger, we have more and more rapid oscillations. Okay. Actually, if the modulus of this term, right, it doesn't matter whether it's plus or minus, there is still an oscillation. So when we see that when modulus E minus E0 divided by h bar by t becomes bigger and bigger, we have more and more rapid oscillations. Okay, so this is a rapidly oscillating function for let's say large values of time. Okay, all right. So what's the problem with rapidly oscillating functions? All right, this can be easily understood. Let's look at an example here. All right, suppose we have got something like a slowly varying function. Okay, let's call this as f of e, and let's say that we have a rapidly oscillating function also. Okay, a rapidly oscillating function of this form. Okay, it oscillates between -1 and +1. Let's say it oscillates between -1 and +1. Okay, now we are integrating the product. Let's say that we want to integrate the product of these two functions. Right, we need to integrate the product of these two functions. So let's take a small region. Let's consider first a small region. Okay, so in this region, this function has practically a constant value. Okay, f of a here, it has a constant value. Let's say that this constant value is 10, for example. Okay, but you see that at each of this point, the oscillating function has a different value. All right, at every point, the oscillating function has a different value than 10. And how is it different? Look, let's say, for example, this point. All right, at this point, our slowly varying function has a value 10, but our oscillating function, let's say that it has a value 1. But at the very next point, or after, let's take another point. At another point, we see that the oscillating function has a value uh, -1. Okay, so even for the range where this function has a constant value, this function is oscillating rapidly between -1 and +1. Okay, so when we multiply, corresponding to this point, the product of functions will give us a +10, and to this point, you will get a -10. Okay, so in that way, corresponding to every positive value, there will be an equal and opposite negative value. So if we add up, if we integrate this function, the product of these functions in this region, it is going to be equal to 0. Now this is true for all regions. This is true for all regions. So if we integrate the product of a normal function, what is a slowly varying function, okay, with a rapidly oscillating function, the integral is going to be 0 because these oscillations will cause strong cancellations. Okay, I think the idea is clear. Why it causes a strong cancellations? I hope it is clear. Okay, so we see that as t becomes large, the integrand oscillates very rapidly unless the energy interval E minus E0 is small considered with h bar divided by t. Okay, so what's the only way to make this integral non-zero? The only way to make this integral non-zero is to have this function not so rapidly oscillating. Okay, we don't want it to be rapidly oscillating, this function. Okay, so this correlation amplitude has a non-zero value, or it has a considerable value only if it is slowly oscillating instead of rapidly oscillating. And when does it become slowly oscillating? When this value is small, whether positive or negative. So let's say that it is slowly oscillating when E minus E0, the modulus of E minus E0 is small when compared to h bar by t. Okay, let's say it's less than h bar divided by t. And in that case, this term will be small. All right, then the oscillations will be slow, and so there won't be any strong cancellation. Okay, so the energy interval modulus E minus E0 has to be small compared with h bar by t if this integral has any considerable value. Okay, so there won't be any considerable correlation amplitude if this function is rapidly oscillating. Okay, let's start from t equal to 0. If time is equal to 0, then this exponential is simply 1. This exponential is also 1. And then we have c of 0 is equal to integral e0 minus delta to e0 plus delta and dE modulus g of e squared multiplied by rho of e. Now what is this? This is equal to 1 by the normalization condition. This is just the sum of the probabilities over all possibilities. Okay, so this is equal to 1. So we see that c of 0 at t equal to 0, the correlation amplitude is maximum. It's equal to 1. Okay. Now what happens as time increases? As time increases, we see that this factor modulus e minus e0 divided by h bar by t also increases. Okay, so that's what we have here. It doesn't matter whether this is plus or a minus. That's why we put a modulus here. So as time increases, modulus E minus E0 divided by h bar by t also increases from 0. Okay. And then this starts oscillating and the correlation amplitude also decreases as this part or as this function increases. Okay, or this phase increases from 0, the correlation amplitude starts to decrease. Okay, so when does it become very small? Right, so we need to fix a limit. Let's say that as this factor increases from 0 to 1, let's say that as this factor reaches 1, when t increases, let's say that this increases from 0, and let's say that when it reaches 1, the correlation amplitude is considerably small. Okay, so we can take this as the limit. This is a limit that we fix. It's a bit arbitrary, but let's fix it. We are not dealing with any exact equalities. Okay, so let's say that the correlation amplitudes become very small when this factor reaches 1 or beyond. Okay, let's fix this as the limit. Okay, so let's say there won't be considerable correlation amplitude when E minus E0 is approximately equal to h bar divided by t, because this can also be written as modulus E minus E0 is approximately equal to h bar divided by t. Okay, so when h bar divided by t becomes approximately equal to modulus E minus E0, then the correlation amplitude becomes considerably small. Okay, so there's a modulus here. So let's say that there won't be a considerable correlation amplitude when modulus of E minus E0 is approximately equal to h bar divided by t. That is, the correlation amplitude decreases as the phase goes from 0 to 1 and becomes small beyond the value of 1 for the phase. Right? So this becomes very small, considerably small, uh, beyond this value, beyond modulus E minus E0, approximately equal to h bar divided by t. Okay, so for considerable correlation amplitude, we have the condition modulus E minus E0 is something like h bar by 2 is approximately equal to h bar divided by t. Sorry, h bar divided by t, not 2, h bar divided by t. Okay, so this is the condition for any considerable correlation amplitude. Okay. So the condition for any considerable correlation amplitude is modulus E minus E0 is approximately equal to h bar divided by t. But we are not done yet. If the energy interval for which this condition holds is much narrower than delta E, okay, then we get essentially no contribution to C of t. Why is this? Because here also there is a function. All right. So let's draw this function like this. We have it like this. It's 0 far away from E0 on both sides. Okay, so this is E0. We said that it has a width that we call as delta E. Okay, now if this condition holds only for a small range of energies, let's say it holds only for a small range of energies here, right? Then everywhere else there would be rapid oscillations, and again there won't be any considerable contribution to C of t. Okay. So for any considerable contribution to C of t, this condition should hold for this entire interval, all right, roughly for this entire interval. Okay. So let me repeat, if this condition holds only for a small range of energies, let's say that it's slowly oscillating here, all right, but then it would be rapidly oscillating everywhere else, and then the contribution to the correlation amplitude will become very small. Okay. So again, if this integral should have any considerable value, this condition has to hold for this entire range, all right. What does this mean? This means that this condition has to hold for energies up to, let's say, roughly, all right, we are talking about uh, rough values, all right. The energy, this condition has to hold for E0 plus delta E, let's say plus or minus delta E. Okay. So here, all right, then it would mean that this condition holds for all energy values or most energy values within this region. Okay. Where delta E here is the width of this function, width of the Gaussian. Okay. Now, if we want this condition to hold for energies E0 plus or minus delta E, then E minus E0 corresponding to this will become, this will be E0 plus or minus delta E minus E0. All right, we have taken this as E. So this is equal to plus or minus delta E. Okay, or modulus of E minus E0 will be equal to simply delta E. Okay. So again, for non-zero values or considerable values for this integral, okay, this E minus E0 has to be also delta E. Okay, so the condition now becomes delta E is approximately equal to h bar divided by t. Okay. So finally, we come to the conclusion that for some considerable contribution to the correlation amplitude from this integral, this condition has to be satisfied. Delta E has to be approximately equal to h bar divided by t. Okay, we are not talking about exact equalities here, right? We are just talking about approximate values, right, or approximate equalities. Okay. So the condition for any appreciable amount of correlation amplitude is that we found this condition is delta E has to be like h, it has to be approximately equal to h bar divided by t. Okay, so we can talk about the characteristic time at which the modulus of the correlation amplitudes starts becoming appreciably different from 1. We know that it starts at 1 and it becomes smaller and smaller. So the time at which it becomes appreciably different from 1 can be obtained from here. This means that t is, okay, t is h bar divided by delta E. Okay, so we start at time t equal to 0. All right, at that time the correlation amplitude is 1, and when time becomes h bar divided by delta E, okay, then the correlation amplitude will become appreciably different from 1. Okay. So as we said earlier, the correlation amplitude is maximum at t equal to 0. Here we have chosen, it's somewhat arbitrary, all right, somewhat arbitrarily to say that the correlation amplitude changes considerably when the phase reaches 1. Okay, and when does the phase reach 1? The phase reaches 1 when t is h bar divided by delta E. Okay. So we have the condition t is equal to or approximately equal to h bar divided by delta E. Now we got this equation for a superposition state with a quasi-continuous energy spectrum. Right? We made some assumptions. But this result also makes sense for a two-level system, for example. Earlier we talked about the example of spin precession. We saw that if we start with the state ket Sx plus, it becomes more and more different from ket Sx plus as time goes on. For example, we saw that it will pick up some component along the ket Sx minus direction, etc. In that case, we can find the correlation amplitude, okay, as this inner product. This is the initial state, this is the state at time t. And we found this inner product. This was equal to cos omega t divided by 2. Again, we see that at t equal to 0, the correlation amplitude is 1. And it becomes appreciably different from 1 for the time t is equal to here h bar divided by delta E. In this case, we can write as E plus minus E minus. which is equal to 1 divided by omega. So if you put t equal to 1 by omega here, you get the correlation amplitude is equal to cosine of half. Okay, so cosine of half is different from 1, right? Cosine of 0 is 1. Let's say that it becomes appreciably different from 1 at a time omega, or at a time t equal to h bar divided by e plus minus e minus, or simply t is equal to t approximately equal to 1 by omega. Okay, so we can say that ket Sx plus starts losing its identity after a time of 1 divided by omega, which is also equal to h bar divided by e plus minus e minus. Okay, so this is what we learned. As a result of time evolution, the state ket of a physical system ceases to retain its original form after a time interval of order h bar divided by delta E. Okay, it becomes less and less like the initial state as time goes on, and it becomes appreciably different, appreciably distinct from the initial state at a time of the order of h bar divided by delta E. Okay, now we did all calculations by assuming that t equal to 0. We could also take some t equal to t0, all right? And then instead of t in this expression, we have t is equal to h bar divided by delta E. If we started with some t0, we would have the result as t minus t0 is of the order of h bar divided by delta E. Or simply we can write this as delta t is of the order of h bar divided by delta E. Okay, or we can write this relation as delta E multiplied by delta T is of the order of h bar. Okay, sometimes this relation is also called the energy time uncertainty relation. Delta T multiplied by delta E approximately equal to h bar is also called the energy time uncertainty relation. This is actually a misnomer, right? Because uncertainty we have already used for position, momentum, uncertainty, etc. Or the uncertainty relation for incompatible observables. We have seen this. Okay, we have seen that there's an uncertainty relation between two incompatible observables. All right, this is not an uncertainty relation of the same type that we have seen before. This is a different type of uncertainty relation because time is not an operator here. Okay, so this is something entirely different, but sometimes this is also referred to as the energy time uncertainty relation. Okay, in this relation there's no problem in defining delta E. Delta E can be defined precisely because energy is an observable in quantum mechanics and there is a corresponding Hermitian operator, the Hamiltonian. So we can define delta E just like we defined the uncertainty for any other observable. That is, we can write delta E is equal to square root of the expectation value of h square minus the square of the expectation value of h. This is exactly how we define the uncertainty for any observable. But delta t appearing in this expression, it's not an uncertainty at all. Because there's no Hermitian operator corresponding to time. Time is not an observable like energy, angular momentum, position, etc. And so there's no inherent limit on how accurately we can specify time. Quantum mechanics does not impose a limit on how accurately we can specify time. The delta t appearing in this relation is actually the amount of time we need to wait for the system to change. So this relation actually means that the amount of time needed for a considerable change in the initial state or from the initial state depends on the initial spread in the energy. Okay. For example, if the initial state is an energy eigenstate and not a superposition of energy eigenstates, in that case delta E is equal to 0. Because if the system is in an energy eigenstate, it means that it's in a state with a definite energy. So there's no uncertainty in energy, there's no spread in energy. You can also show that delta E is equal to square root of expectation value of h square minus the square of the expectation value of h becomes 0 if you are calculating this in an energy eigenstate. Now in this case, the time interval delta t required for the state change would be infinite because we have got delta t delta E is equal to h bar, or delta t goes like h bar divided by delta E. If delta E goes to 0, then delta t goes to infinity. In other words, the state won't change at all. if we start with an energy eigenstate. That is, an energy eigenstate is really a stationary state. Instead, if the initial state is a superposition of energy eigenstates, then there is some fuzziness in energy, there is some uncertainty in energy, or in other words, delta E is not equal to 0. And in that case, the time taken for a state change depends on the initial energy uncertainty, or it depends, delta T depends on the energy uncertainty corresponding to the initial state. So if the initial spread in energy is more, then the time taken for a state change is small according to this relation. If delta E is greater, then delta T becomes smaller. Instead, if the initial state is narrowly peaked around a value of energy, then the amount of time needed for a state change increases. So the so-called energy-time uncertainty relation actually tells us that the amount of time needed for a considerable state change depends on the energy uncertainty in the initial state. Okay, I hope this is clear. So we started studying the correlation amplitude C of t is equal to bra alpha ket alpha comma t0 equal to 0 at time t. Okay, the correlation amplitude is defined as the inner product between the initial state and the state at a later time t. And we found that in general situations, this correlation amplitude becomes smaller and smaller. All right, it becomes smaller and smaller as time goes on, which means that this state in general becomes more and more different from the initial state as the time goes on. Okay, and we saw that it becomes appreciably different from the initial state at a time of the order delta t approximately equal to h bar divided by delta E. Okay, we also saw that this is sometimes referred to as the energy time uncertainty relation. Okay, so with that I shall conclude this session. Thank you.